The biology of memory restoration and cognitive vitality, the prospect of aging often carries a silent, pervasive fear that mental acuity will inevitably degrade like a war machine. This narrative suggests that memory loss is a rigid biological destiny, leaving older adults to manage decline rather than prevent it. However, the modern neurobiological perspective fundamentally challenges this assumption. Current understanding of the brain reveals that neuroplasticity is not the exclusive domain of childhood, but remains a dormant capacity throughout the lifespan, waiting for specific chemical triggers to unlock it. By leveraging a precise physiological mechanism, the aging brain can override the circuits of fatigue and distraction that mimic memory loss. This exploration offers a pathway to access those control switches, transforming the brain from a passive vessel into a dynamic, regenerating system through a singular, potent intervention. The neurochemical architecture of alertness, the sensation of forgetting a name or misplacing an item, is frequently misidentified as a failure of storage, when it is often a failure of retrieval caused by insufficient arousal in the brain's attentional centers. Andrew Huberman posits that the brain requires a specific neurochemical cocktail to mark an event as significant enough to remember and to keep the neural pathways clear for access. This state depends heavily on the locus coeruleus, a small structure in the brainstem that acts as a broadcast tower for norepinephrine. When this chemical is released, it functions like a high-contrast filter for the mind, sharpening the signal of immediate experience and dampening the noise of background distractions. The memory reboot relies on manually triggering this system, which tends to become sluggish in older adults not due to cell death, but due to a lack of intense, acute demand. The mechanism of this cognitive restart operates on the principle that the nervous system cannot distinguish between a physical survival threat and a deliberate, self-imposed spike in physiological intensity. When an individual engages in a sudden, deliberate upregulation of their physical state, the brain interprets this as a signal that the current moment is critical. This releases acetylcholine in the basal forebrain, which highlights specific neural circuits for modification, essentially marking them for memory encoding. The 60-second protocol exploits this biology by forcing a rapid transition from a passive, drifting state to one of high alert. It bypasses the psychological resistance to focus, using the body to lead the mind into a state of readiness that is chemically identical to the hyperfocus of youth. In a practical setting, consider a retired academic named Arthur who struggles to retain the details of his morning reading. He finds his mind drifting, the paragraphs blurring into a vague conceptual soup rather than distinct points of information. Instead of rereading the text passively, he employs the physiological reset. He pauses and engages in a brief, intense bout of specific physical or respiratory maneuvering that elevates his heart rate and narrows his visual field. This is not about general exercise, but about a targeted spike in arousal. Within moments, the fog lifts not because he tried harder to concentrate, but because he flooded his system with the neurochemicals required for concentration. The text becomes sharp again, and the information adheres to his memory because his brain is now chemically primed to record it. However, it is crucial to understand that this system has limitations and cannot be sustained indefinitely without periods of recovery. The brain is not designed to maintain peak norepinephrine release for hours on end. Doing so leads to anxiety, jitteriness, and eventually, a crash that impairs memory further. The protocol is a pulse, not a steady state. Attempting to force this high alert mode continuously throughout the day would deplete the very neurotransmitters necessary for the effect, leading to diminishing returns. It is most effective when used as a surgical intervention, a tool to be deployed when the mind feels particularly slippery or when a specific task demands absolute retention. This understanding shifts the definition of memory issues from structural problem to a state management problem. Many seniors experience senior moments not because their hard drive is full, but because they are operating in a state of low physiological arousal that prevents efficient file retrieval. The reticular activating system, which filters incoming data, defaults to a sleep-like mode in the absence of novel stimuli. By manually shocking this system into wakefulness through a 60-second intervention, the individual reclaims the ability to decide when they need to be sharp. It is a transition from being a passenger in one's own mind to becoming the driver, regulating the flow of neurochemistry with precision. The biology of aging often involves a subtle drift toward parasympathetic dominance during the day, which fosters relaxation but dulls the edge required for sharp cognitive encoding. While relaxation is vital for health, it is antithetical to the formation of crisp, new memories. The reboot exercise serves as a temporary, controlled shift into sympathetic dominance, the fight-or-flight system, harnessed for cognitive utility rather than survival. This controlled stress response mobilizes glucose from the bloodstream into the brain, providing the immediate metabolic fuel that neurons need to fire rapidly and synchronously. It is this metabolic surge that underpins the sensation of the fog lifting and restores the speed of processing that many assume is lost forever. Often, the aging individual accepts a slower processing speed as a new normal, adjusting their lifestyle to accommodate this perceived deficit. They may avoid complex tasks or social situations where quick recall is necessary, which only accelerates the decline through disuse. A more empowered approach involves recognizing that the machinery for speed remains intact, but requires a stronger starter motor to engage. The 60-second reboot acts as that starter motor. By regularly engaging these circuits, the individual maintains the plasticity of the locus coeruleus and its connections, ensuring that the brain remains responsive to demands for focus rather than atrophying into a permanent state of low-resolution processing. Neural plasticity, the brain's ability to rewire itself, is triggered by the coincidence of focus and urgency, both of which are chemically mediated. When the reboot protocol is executed, it creates a window of high plasticity that lasts for several minutes to an hour. During this window, whatever the individual focuses on is more likely to be encoded into long-term memory. This creates a powerful leverage point. The 60 seconds of effort yields a disproportionate return in cognitive durability. It transforms the act of remembering from a passive hope into an active, biological construction project. Where does the hesitation to engage fully stem from? The visual anchoring system, the relationship between the eyes and the brain, is far more intimate than mere observation. The eyes are essentially the only visible part of the central nervous system. Huberman emphasizes that visual focus is the primary driver of cognitive focus. When the eyes move randomly or scan the environment without locking onto a target, the brain remains in a mode of surveillance rather than analysis. To reboot memory and attention, the individual must harness the mechanism of overt visual attention, which physically narrows the aperture of perception. By fixing the gaze on a single point for a sustained period, the brain receives a bottom-up signal to suppress off-target neural activity, quieting the internal noise that disrupts memory formation. This visual locking mechanism triggers a cascade of neural synchronization that prepares the mind for data intake. When the eyes are steady, the brainstem sends a signal to the prefrontal cortex to align its activity, creating a clear channel for information processing. In an aging brain, the muscles that control finite movements can become less disciplined, leading to more frequent, microscopic drifts in gaze that fracture attention. The 60-second exercise involves a deliberate overriding of this drift, forcing the eyes to hold a static position. This physical stillness translates directly into mental stillness, halting the chaotic attentional blinks that create gaps in memory and understanding. Consider the case of Elena, a grandmother who enjoys learning languages but finds that new vocabulary slips away almost instantly. She often studies while looking around her room, checking her phone, or letting her gaze wander out the window. By applying the visual anchor principle, she changes her approach. Before she begins a study session, she spends 1 minute staring at a specific mark on the wall, suppressing the urge to blink excessively or look away. This visual discipline acts as a gating mechanism. When she returns to her vocabulary list, Her brain is locked into a focal mode. The words are no longer just passing through her visual cortex. They are being scrutinized by a hyper-focused attentional system that was primed by the gaze exercise. It is important to note that this type of visual fixation is metabolically expensive and can be tiring. The brain naturally resists maintaining a static gaze because it evolved to scan the horizon for threats. Therefore, individuals with high levels of anxiety or those prone to migraines might find intense visual fixation uncomfortable or counterproductive if pushed too far. The goal is not to strain the eyes to the point of pain, but to exert control over the oculomotor system. If the practice induces a headache or significant discomfort, it indicates that the duration should be shortened or the intensity reduced. The objective is neural recruitment, not ocular strain. The connection between vision and internal state is bidirectional. Just as stress narrows vision, narrowing vision can induce a state of heightened alertness. This is the physiological lever that the 60-second reboot pulls. By voluntarily narrowing the visual field, the individual manually engages the sympathetic nervous system's alertness pathways. This is distinct from the stress of a deadline or a danger. It is a eustress or positive stress that invigorates the mind without the corrosive effects of chronic cortisol. For an older adult, this tool provides a way to generate the energy needed for a conversation or a task without relying on external stimulants like caffeine. There is a profound link between the visual system and the vestibular system, the balance center of the inner ear. Huberman often discusses how movement and balance interact with vision to calibrate the brain's alertness. When an individual combines visual fixation with a challenge to their balance, such as standing on one leg, the brain must recruit massive amounts of neural resources to maintain stability. This recruitment activates the cerebellum and the cortex simultaneously, effectively waking up the entire neural network. The 60-second exercise can thus be multimodal, combining a fixed gaze with a postural hold to maximize the wake-up signal sent to the memory centers. In the context of longevity, maintaining the precision of the visual system is a proxy for maintaining the precision of the mind. The deterioration of one often parallels the other. By training the eyes to hold steady, the individual is effectively training the brain to hold a thought. This prevents the cognitive drift that characterizes age-related attention deficits. The ability to inhibit the impulse to look away is the same neural machinery used to inhibit the impulse to think about something else. Strengthening this inhibitory control is central to preserving the integrity of working memory in later life. Furthermore, the visual system dictates the brain's perception of time. When focus is narrow and high contrast, the brain processes more frames per second, making time feel expansive and detailed. When focus is panoramic and relaxed, time seems to compress. By utilizing the visual anchor, the individual shifts into high-resolution time processing. This allows for better encoding of the sequence of events, which is often what is lost in memory lapses. The person remembers not just the fact, but the context and the order, which are crucial for recalling the narrative of one's day. Why do I avoid looking directly at the things I need to focus on? The respiratory driver of state change respiration acts as the remote control for the autonomic nervous system, offering the most direct access to the brain's chemical state. Huberman highlights that the pattern of breathing dictates the ratio of oxygen to carbon dioxide in the blood, which in turn regulates neuronal excitability. A pattern of rapid, deep breathing, often termed cyclic hyperventilation, rapidly offloads carbon dioxide and increases the pH of the blood. This alkaline state causes a slight constriction of blood vessels in the brain and signals a state of urgency to the nervous system. This respiratory shift releases adrenaline, not out of fear, but as a resource for action, instantly clearing the cobwebs of lethargy that dampen memory access. The 60-second reboot leverages this respiratory mechanism to jolt the system out of a hypometabolic or sleepy state. For many older adults, breathing becomes shallow and efficient, optimized for rest, but insufficient for peak cognitive demand. By engaging in a minute of vigorous, deliberate inhalation followed by passive exhalation, the individual manually spikes their alertness. This is not about hyperventilating to the point of passing out, but about generating a transient stress response that mobilizes energy. The subsequent retention of breath or a long exhale then calms the system, allowing that mobilized energy to be directed toward a mental task rather than physical agitation. Imagine a scenario involving Robert, who is preparing to manage his finances, a task that usually makes him feel drowsy and overwhelmed. His brain associates the task with boredom, leading to a shutdown of attentional resources. To counter this, Robert sits in his chair and performs 20 to 30 forceful inhales through the nose, followed by short exhales. He feels a slight tingling and a rush of heat, signs of adrenaline release. Immediately following this 60-second burst, his eyes snap open wider, and his mind feels crisp. The respiratory maneuver has chemically slapped his brain awake, providing a 10 to 15-minute window of heightened executive function where he can process the numbers without fatigue. It is vital to acknowledge that this respiratory intensity is a stressor and may not be suitable for everyone, particularly those with panic disorders or severe cardiovascular issues. The sensation of lightheadedness or tingling can be interpreted as anxiety by those unfamiliar with the physiology. Therefore, the protocol must be approached with a mindset of exploration rather than force. The aim is to find the minimum effective dose to shift the state, not to induce a panic attack. If the intensity feels overwhelming, slowing the rhythm or reducing the depth of the breaths allows the individual to retain control while still harvesting the benefits of increased alertness. The connection between breathing and memory is also anatomical. The rhythm of respiration influences the electrical activity of the hippocampus, the memory center of the brain. Research suggests that inhalation synchronizes the oscillations of the limbic system, optimizing the timing for memory encoding. By taking control of the breath, the individual aligns these neural rhythms, creating a coherent electrical environment for storing new information. This is why memory recall is often sharper during the inhalation phase of the respiratory cycle. The 60-second exercise amplifies this natural synchronization, creating a powerful, rhythmic driver for neural encoding. Furthermore, the carbon dioxide tolerance of an individual is a strong indicator of their stress resilience and cognitive buffering. By training the system to handle the fluctuations in blood chemistry induced by the breathing protocol, the aging brain becomes more robust against stress. Instead of shutting down under pressure, the brain learns to maintain function. This resilience is critical for memory, as stress is one of the primary destructors of hippocampal cells. Controlled, voluntary stress through breathing inoculates the brain against the uncontrolled, chronic stress that erodes memory over time. This respiratory intervention also serves as a bridge between the body and the mind, proving that cognitive states are physically negotiated. The lethargy that often accompanies aging is frequently a respiratory habit of shallow, low-volume breathing. Breaking this habit, even for 60 seconds, reminds the nervous system of its capacity for high-output functioning. It flushes the system with oxygen and signaling molecules that promote wakefulness, effectively turning up the dimmer switch on consciousness. The result is a brain that is not only awake but alive and ready to engage with the complexity of the world. What sensation in my body am I interpreting as fatigue when it is actually stagnation? Synaptic consolidation and long-term retention, the final phase of the memory reboot, is not the activation itself, but the recovery and consolidation that must follow. Huberman asserts that while alertness triggers the marking of neurons for strengthening, the actual wiring of the memory occurs during periods of deep rest. The 60-second exercise is the trigger, but the stabilization of that memory happens when the system returns to calm. Therefore, the protocol is incomplete without a subsequent period of non-sleep deep rest, NSDR, or high-quality sleep later that night. The intense focus generated by the exercise must be balanced by a deliberate decoupling from engagement to allow the brain to print the information onto the neural architecture. This biological rhythm of pulse and pause is essential for the aging brain, which may require longer recovery times to consolidate synaptic changes. After the heightened state of the reboot and the completion of the mental task, the individual should engage in a brief period of unfocused relaxation. This could be staring at a horizon, closing the eyes for a minute, or simply letting the mind wander. This downtime allows the hippocampus to replay the neural sequences that were just activated, transferring the data to the neocortex for long-term storage. Without this recovery phase, the chemical spike of the reboot may result in temporary clarity, but fail to produce lasting memory retention. Consider a senior student of the piano, Margaret, who uses the reboot protocol before practicing a difficult piece. The breathing and visual focus help her nail the complex finger movements during the session. However, to ensure she retains this skill for tomorrow, she finishes her practice and immediately sits on her porch for 10 minutes, doing absolutely nothing. She resists the urge to check the news or call a friend. This do-nothing phase is biologically active. Her brain is busy rapidly replaying the motor sequences she just learned at high speed. By respecting this biological need for consolidation, she ensures that the effort of the practice session is locked in, preventing the frustration of having to relearn the same passage the next day. A common counterargument is that older adults need constant stimulation to keep their minds sharp, and that rest equates to rust. However, the neurobiological reality is that constant noise prevents the signal-to-noise ratio required for memory. Continuous stimulation without deep rest leads to a shallow processing of everything and the retention of nothing. The reboot protocol is powerful precisely because it creates a high-contrast peak of activity, which must be framed by valleys of rest. It is the dynamic range, the difference between the highest alert state and the deepest rest state, that signals health and vitality in the nervous system. The 60-second reboot is ultimately a tool for agency. It reframes memory not as a passive library that is slowly losing its books, but as a dynamic recording studio that requires a specific power supply to operate. By mastering the controls of vision and respiration, the individual steps out of the passive decline narrative and into an active role of neural stewardship. The aging brain is not necessarily a broken vessel. In many cases, it is simply a vessel that has stopped receiving the intense signals required to keep its machinery oiled. Providing those signals manually restores the function. This approach validates the concept that vitality is a practice, not a trait. It requires the willingness to endure brief moments of discomfort, the strain of focus, the intensity of breath, to purchase hours of clarity. It demands a rejection of the comfort of lethargy. The memory reboot is a microcosm of a larger philosophy, that the biological systems of the body, no matter their age, respond to the language of demand. When the demand is clear, intense, and followed by rest, the body and brain adapt. The promise of this protocol lies in its accessibility. It requires no equipment, no pharmaceuticals, and no cost. It only requires the knowledge of how the machine works and the discipline to pull the lever. In doing so, the individual reclaims the narrative of their own aging, moving from a story of inevitable fading to one of deliberate, rhythmic pulsing of life and light. The memory is there. It is simply waiting for the command to awaken. Am I willing to endure 60 seconds of intensity to reclaim my clarity?